Recording started. All right, these last two chapters of this book are actually pretty good. I mean, talking about process control theory. Control theory is okay. It'll probably help you understand the bigger lab that y'all are doing this semester and probably into next semester. But the goal of process control is just to turn raw materials into a finished product. And that all that is to say, like y'all been messing, or some of y'all been messing with pressure transducers. Next semester, you're gonna mess with temperature indicators, which could be a thermocouple. And you're just taking that raw data, which we talked about thermocouples, like what a thermocouple gives off. Thermocouple gives off a millivolt DC. So that's a raw signal, and process control is just turning that raw signal into an actual temperature an operator can see on their control panel. So that's the goal of process control. Everybody made it in their book to modulate.
Open it up now.
Okay. Some of the trade terms, I don't have any of them highlighted, but excuse me. There's going to be a few of them that are pretty good to know. Error signal, manipulated variable. So you should know what a manipulated variable is. Process parameter that's regulated by the final control element. So the manipulated variable would be like the level of a tank, like opening and closing a valve to let water into a tank. You in? Did you say you're in the test?
No, they say to wait.
So we know you're in there. My first highlight is the first two sentences on page 1. Process control is the study of manipulating material to produce a desired product. More specifically, it is the application of a control system to a process in order to provide the most efficient and reliable operation possible. Process characteristics 110, so bottom right of page 1. I've got the first two sentences there highlighted. A major consideration of any process control system is the process itself. A process may be defined simply as the operations used in the treatment of a material. So whether that be oil, gas, water, corn, stuff like that, anything can be used in a process. It's just a matter of how you're measuring it and stuff like that. Like I would never measure like a grain silo with a pressure transducer, because you can't get a full pressure on that. You have to measure it with an ultrasonic level detector or some sort of equivalent. Page 2. It's talking about energy. Energy, down where you see the energy equation, I've got that equation in the sentence right above it highlighted. So the sentence right above, so all the way in the bottom left of page 2, therefore, whether the individual parameters of the process are constant or changing in value is determined by the energy balance equation, which is energy out is equal to energy in minus energy lost plus energy stored. So if I had everything has an energy equation, right? Even what's that?
It's going to get in the car. Here. Car.
Yeah, I haven't authorized it yet because you weren't in there yet. Make sure put the right person in. Is the test popping up? Yeah, it won't let you hit start. Try to refresh your screen. I'll just leave it for a second.
I want to close this one. Okay, here. Yes, no, proceed.
All right, you should be good. Everything has an energy equation. So like a car, what would be the energy you put into a car? Gas. You have gas going in. So what's your energy out of a car?
The movement is going.
Movement of a car. So energy out, so the movement is going, takes gas to do that. What would be your lost energy in a car? It's all kinds of them.
Yeah, pretty much a waste. Any gasoline that doesn't get burned correctly.
Right. Major one. Anybody know the efficiency? If I show that efficiency rate of a internal combustion engine? 50%. They are 50. So their energy equation, you take the amount of energy you can get from so much gas to the energy amount of movement you can get, and we're losing 50% of that going from gas to movement. That's why, like, there's a lot of people that debate the electric car thing. Electric cars are coming. Do you know what the efficiency of an electric motor is? About 95% of a good electric motor. That's why, like, gas and stuff like that is getting so low, like it's hard to make, and it deteriorates the ozone, stuff like that. Like, whether people think of it or not, but using a battery in an electric motor is a much more efficient way of turning one type of power into movement. But anything's going to have heat. Heat is one of the biggest. What you want to eliminate is your energy loss. So heat loss is one of your biggest energy losses in your energy balance equation. But everything, you just have to know that everything has to balance out. So energy in minus lost and stored has to equal your energy out. So you have to know that equation. Good. Top right of page 2, that paragraph in the top right, I've got the 4th sentence highlighted. Any disturbance to the energy in, energy out, energy loss, or energy stored will upset the balance and consequently cause a change in the values of process parameters. So any disturbance, so if you're driving a car in like a windstorm or something like that, whether it's pushing you from the back, side, or front, that's a type of energy that is going to affect that energy equation. Make sense? Process control system 120. Everybody know how a heat exchanger works? I mean, you'll mess with them next semester on the big trainers, but essentially you put hot water inside of the heat exchanger. There's a bunch of tubes or coils. So hot water goes in, flows either on the out. Usually the water is flowing on the outside, like I don't know, outside of the tubes and stuff. The cold oil will flow through the tubes and come out the other side, and then the hot water is all around those. So you're heating up the oil without actually touching the two together. So you can do that with anything. The trainers in there just do it with water. You're transferring hot water to cold water, and you're transferring, you're taking that energy and transferring it. Button 120, process control system, bottom right of page 2, second paragraph, second sentence. the process parameter that is selected for control is called the controlled variable. So this is a pretty good slide right here. Controlled variable is the process parameter that's being kept in balance. So that would be if I had a tank and I wanted to keep the level in the tank a certain level, our controlled variable is going to be the level. The measured variable, the current value of the controlled variable as reported by a sensor. So a measured variable doesn't necessarily have to be the controlled variable, because you can have, like, you have a pressure transducer on the bottom of the tank. You're putting pressure on that transducer, however much pressure that is, it can turn that into a level. So that's your measured variable. Set points wherever you want it. Error is going to be the difference. And manipulated variable, that's going to be variable that the control system adjusts to rebalance the system. This is you're adding control to your heat exchanger. So your hot water in is now being controlled by a pneumatically controlled valve. So 2 dashes mean pneumatics. And then this little mushroom head right here means this is a control valve. So hot water is coming into the control valve. The valve's being, it has a temperature controller right here, temperature transmitter, and thermocouple right here. So thermocouple is going to the transmitter, which is going to the controller. Controller is seeing what the temperature of the hot oil coming out is. If it's not hot enough, it's going to open this valve even more and let more hot water flow through here to get the temperature up. If it's too hot, it's going to shut this valve off a little bit more, and the oil is not going to be as hot coming out. Does that make sense? So this is your control loop right there. Page 3, the second full paragraph, or the paragraph in the bottom left of page 3, second sentence is highlighted. A controller is a device that operates to ultimately regulate the controlled variable. So it kicked you out? Is it letting you hit start again? So just kind of like I went through, sensors monitor the controlled variable. Controller calculates the error. So the error is what the set point is versus what the actual variable is. Sends that to the valve and alters the manipulated variable. Top right of page 3. I've got a sentence right in the middle of that paragraph highlighted. The final control element regulates a parameter of the process so the controller can regulate the control variable. More often than not, that is a pneumatically controlled valve. Right now, a lot of them are going to motor controlled valve, but still quite a few pneumatically controlled valves. Next paragraph. I've got the last sentence in the next paragraph highlighted. The manipulated variable is used by the control system to supply energy or material to the process to regulate the deviation of the controlled variable from the desired value. So what's our energy in with this control system?
Part that's going into the exchanger.
Well, we got the oil going in here and the hot water going in here. What's our energy in? The oil or the hot water?
The hot water.
The hot water. Hot water is a form of energy, like it's hot. So our loss is going to be like the frictions going through the tubes, or some of these tubes can get crushed or stuff like that. Or if this pipe right here is uninsulated, the heat can get out of these pipes. So remember our energy equation: energy in minus energy lost plus energy stored. So even those tubes can store energy. Our energy out all the way at the end is going to be how hot this oil is. We're also going to have a loss for cold oil. Cold oil is going to be considered a loss. Page 4. 130 components of an instrumentation channel, detectors and sensors. 131. In detectors and sensors, first paragraph, last two sentences are highlighted. The measured quantity is always disturbed by the act of measurement. A good instrument is designed to minimize this disturbance. So all detectors are going to interfere with the process somewhat. Like we've talked about an orifice plate, right? Orifice plate can be used to measure flow because it puts in a pressure differential in a pipe because it has, everybody remember what orifice plate is? It's the plate with the little circle in it. So you get a high head pressure on one side, low pressure on the other side. And that's what it's talking about. It's introducing a disturbance into the process. So most stuff is going to introduce some sort of disturbance in the process. So that's going to be part of your energy loss, but you have to do that in order to detect whatever you're trying to detect, whether it's temperature. This is a pretty good chart on page 5 and 6, going on to 7, for the different variables and like how to measure them. So temperature, bimetallic strip. So anybody remember what uses a bimetallic strip? For example, anybody ever use a meat thermometer, cooking or grilling or something like that? Put a meat thermometer, that's a bimetallic strip. So that's a metallic strip with 2, bi means 2. So two different types of two different dissimilar metals that expand at different rates. And whenever you put something hot or cold on them, they expand, and then that's what turns the dial on top of the thermometer. So that's a bimetallic strip. Thermocouple is just a 2-wire that creates a DC millivolt. RTDs, thermistors. You can read through. I would recommend reading through these. They have the pressure. There's a lot, just diaphragm, bellows. I think we talked about those. Board on tube. Board on tube is what most pressure gauges use. Leveler, differential pressure, which y'all will do all the way at the end of the T5552. Bubbler. If I talked about a bubbler before and how a bubbler measures level. So if you had a bubbler just essentially just puts a pipe into a tank and blows air through it, and the amount of resistance to blowing the air through it can determine a level. So if you think about it, if you took a straw and a big glass, you just put the straw in there with empty glass and you blew into it, it'd be pretty easy, right? Put half a glass of water in there, it's a little bit harder to blow through the straw. Full glass of water, even harder to blow. Not hard, but it's a little bit harder. So that's how a bubbler works to tell level. However hard that head pressure is to push air into that system, it determines a level based on that. So they're actually pretty good for turbulent tanks. Like a lot of times you can have a tank the size of this room that's being filled from the top, and like water or whatever is just flowing into it, and the top is pretty turbulent. It's not good to have a float in there because that float's going to be jumping up and down, moving stuff around. But you can put a bubbler, just a pipe that comes in, goes all the way to the bottom, and down near the bottom it's not as turbulent. So then the turbulence doesn't affect a bubbler. So there's a bunch of different types of detectors and stuff, and they talk about the operations and how they work. I would recommend reading through that, especially the flow portion. I know you're going to use an orifice plate, an interior tube, and a pitot tube, also a turbine flow meter, all on that trainer out there. So you just need to know it's like there's a bunch of different ways to skin a cat. There's a bunch of different ways to measure these different parameters. Page 7, 132, transducers. It's the sentence right in the middle, right after where you see figure 3 in the first paragraph of 132. A transducer receives one form of energy and converts it into another form of energy. So on that process tank out there, what type of transducer have y'all been using? Josh and Eric. It's actually P to I. It's taking in a pressure. You are using I to P transducer for the valve, but on the bottom of the tank that you were just messing with, that pressure transducer, that's taking the pressure that the water is putting onto that transducer and turning that into a 4 to 20 milliamp signal. So it's taking pressure in and outputting a current. So it's taking in one form of energy and outputting a different form of energy. Transducer. That should be an easier one to remember. Amplifiers and signal conditioners. These are getting, I don't have any highlights in 133, but these are getting more and more rare. You're not going to see amplifiers too much because a lot of times they're figuring out ways to use lower voltages or amperages or put an amplifier into the transmitter itself. I'm surprised I don't have anything in transmitter. You can have transmitters for temperature, pressure. Differential pressure transmitter is going to be for, you can use that for level or pressure. I don't have anything transmitter. Page 8. You're going to have your common types of transducers. So what have I told you all along is the most common type of transducer?
4 to 20 milliamp.
That's the most common type of signal. But transducer, converting what form of energy into another? An I to P. Taking in it's like the control valve. You're sending that control valve a 4 to 20 milliamp signal, and that's turning that into a 3 to 15 PSI in order to close that valve. So I to P transducer is going to be your most common. You're going to need to highlight table 2. You're going to have a question come out of table 2 on the module review all the way at the end. Controller 135. Second sentence of controller is highlighted. There are 3 basic types of controllers: mechanical, pneumatic, and electronic. More often than not, electronic controllers are what people are using now. 140, still on page 8. I've got most of that first paragraph or most of what's left on page 8 highlighted. My first one is the first sentence. A control valve is simply a variable orifice that is used to regulate flow of a process fluid according to the requirements of the process. The next highlight is the next sentence. In a control valve, an actuator that is connected to the valve plug stem moves the valve between open and closed positions to regulate flow in the process. And then the last sentence on page 8 is also highlighted. There are 2 basic categories of control valves: gate valves and globe valves. Gate valves are used for what type of control? Anybody remember that?
On off.
On off, good. And globe valves can be used for regulating flow. Gate valves should not be used for anything besides on off, because it can tear up those seats on the bottom of the gate valve. Every plant I've ever been in uses gate valves for control valves, and it shouldn't, but should. I don't have anything else on pages 8 and 9. Flipping over to page 10. You've got the manual actuators. That's just where you have a little screw on top of some of your valves where you can manually set them to not go below a certain point. I don't think I don't have anything highlighted in that. Solenoid actuators, 142, this is an online test question. This will be the only place you see it. 142, second paragraph, first sentence. The solenoid consists of a valve body, a magnetic core attached to a valve stem, and a solenoid coil. Everybody remember what a solenoid coil looks like? You go grab one. Did y'all do the AC/DC trainers, Mr. Wally?
Yes, sir.
Yeah, you don't mess with this. So this is a solenoid core is essentially what it is, but it can also be a valve. So you remember whenever you put current through this, this is just a coil of wire, induced a magnetic field, then took this and sucked it in there, right? So a solenoid valve works the same way. It can be open as soon as I energize it. It can slam it closed and shut off, turn on or off, flow through that pipe. That makes sense? So just very simple piece of equipment. But you'll deal with those, or y'all are dealing with those in the process trainer. But that was an online test question. Pneumatic control valve actuators. I don't have either 1, 4, 3, or 4. I don't have any highlights in those. Yeah, I think we're gonna mess with those enough to where we'll have to talk about those. Go on to page 12. So page 12, 145. Valve positioners. The first two sentences of 145 on page 12 are highlighted. A valve positioner is a device used primarily to maintain the control valve plug at a position that is directly proportional to the controller output. To perform this function, the stem motion of the valve actuator is compared to the signal from the controller. So this is a valve positioner. So you can mount this to a valve. If you look at that big tall valve over there, you can see the two screw holes in the front of it, right on the bottom side of that red spring. There's actually there's a bracket that you connect this to. This is electronically controlled positioner, so you can set up the signal going back to the controller. But essentially what you do is you slap this on the valve, and then everybody see this little arm right there? That arm is connected to the stem going up and down. So it starts right in the middle. Whenever the valve opens, it goes up. Whenever the valve closes, it goes down. So this is what sends a signal back to the controller saying what position the valve is in, right? And then it can, whatever the set point is, it can actually change the air pressure going into the valve to make it be whatever the controller wants it to be. So the valve itself is just dumb, like it doesn't have any electronics or anything like that on it. This is what you connect to a valve to talk to a PLC or some type of controller to send an analog signal to where you can manipulate the valve to different positions, whether that be 25, 50, 75% open, 100% open, something like that. Does that make sense? So you have different types of positioners. This is an electronic one. I've got a pneumatic one, which are both of these are still pretty old, but a lot of them are going to more of the electronic 4 to 20 side of things. I think what I'm going to do in order to just keep going, like I'm going to give y'all everything for homework. Are you good with just doing all the section reviews for homework? I just keep going. All right, I'll do that. All section reviews module review practice test or what's gonna be homework, and I'll just keep going. We'll go over all that. Next week. It's just is a lot. Four sections. No, we'll just keep going. Control loops. Some of the trade terms are good to know. Closed loop, open loop. Those are the two big ones. Open loop, probably at the end of my. Josh, you remember doing the open loop tuning all the way at the beginning of the lab you're on? Remember opening up that valve a little bit and trying to get the output set just right to where it would keep up with condensed water? So that's called open loop tuning. So that's looking at where the level is, making an adjustment, going back and looking. You are acting as the controller. So if you are acting as a controller, it's an open loop. So I mean, you're thinking about it like your loop is like this, and then you're right there. Like it's not closed. There's no type of control or anything like that. Closed loop control, you're gonna add in a PLC or something like that. So if I had a say it was just a big tank of water, I would have a DP sensor right here, measuring the level. I would have my controller right here. So that's measuring the level. And then I can have my pneumatic valve right here. So this would be a closed loop. So it's reading the differential pressure, saying what the level is. If the level is different, it can go to the pneumatically controlled valve and open it up to add more water or whatever you want to do. But open loop, closed loop, two different things. My first highlight on page 15 is the last sentence of the first paragraph is an online test question. So managing the interactions among the devices in the instrumentation channel is the function of the instrumentation control loop, which ultimately determines the process control stability. You want to key in on control loop. The next paragraph is highlighted. 4 basic types of process control loops common in the instrumentation industry are feed forward control, most commonly referred to as open loop, feedback control, closed loop, cascade control, and ratio control. We've got open, closed, cascade, and ratio. Eric, the first paragraph, last sentence, managing the interactions among devices in the instrumentation channel is the function of the instrumentation control loop, which ultimately determines process control stability. That's an online test question.
Okay.
And then the next paragraph is highlighted as a question. 210, feed forward, so open loop. First sentence is highlighted. If the control variable measurement is not used as a signal to drive a controller, adjust the input to the process, the loop is considered to be open loop controls, an open loop control system. The next sentence is also highlighted. When open loop control is used in industrial applications, it's often referred to as feed forward. So feed forward and open mean the same thing. Feedback and closed loop are the same. The last paragraph in 210, the whole thing's highlighted. With an open loop control system, every input variable must be kept constant in order to keep the control variable constant. Some inputs such as ambient temperature and the temperature of hot water entering the shell side of the exchanger may not be measured or controlled, resulting in the need for manual adjustment. Key in on manual adjustment of the system. So open loop is going to use manual adjustment. So if you're looking up here, feed forward, open loop. So what's our control variable? What are we trying to control in this loop? Temperature of what?
Temperature of the hot oil.
Of the oil. So this is our end goal right here, is to get hot oil coming out at a certain temperature. But in this loop, they are not plugging this temperature recording into any of our controls, right? So they're just putting a set point into this, a set point into this valve, and our cold oil coming in here, and they're just saying set this at whatever the temperature should be. But you're gonna have to monitor this, and then maybe change your hot water coming in or something like that. Whenever your temperature is not a part of your controller, or whenever your final end goal is not a part of your control, that is open loop. Feedback control 220, all the way at the end of page 15, first sentence. Another term that's associated with closed loop control system is feedback control. Page 16, that last sentence in that first started paragraph is also possible, or is also highlighted. There are two types of feedback possible. Positive feedback and negative feedback. They go through the operation of the closed loop control, but essentially what we're doing here, cold oil going in here, hot oil going out. Thermocouple measures the temperature of the oil, temperature transmitter sends it to controller does the calculations, sends that to the control valve, or does calculations and sees what the error is between your set point and your output, and then makes an adjustment to the control valve based on that. Good. I do have a highlight in 221 on page 17, that first full paragraph on page 17. It's the third to last sentence in that paragraph. An analysis of the response highlights one of the major flaws of the closed loop control. A change in the control variable has to occur before any response can begin. So there has to be a change in your thermocouple for any change in the control valve to happen. Performance of closed loop control, 222. First sentence of 222 is highlighted. Primary performance criterion for any closed loop control is stability. The goal of closed loop control is always to get to the set point and remain around the set point, right? Stability. So the slower stuff can happen, the better. Page 18. And still talking about performance. The second paragraph on page 18, last sentence. The tendency for increasing amplitude oscillations can be a major limitation of closed loop control. So essentially what that's saying is, yeah, time, and we'll just stick with level. And this is our 0 point right here. So if I was wanting to say I had a tank and I wanted the level to be set at 100 gallons, right? And I'm starting at 0. So that's my what?
Set point.
That's my set point. So if I start at 0, my signal to my valve initially is gonna tell my valve, my control valve to do what?
Switch open, 100%.
All the way open, 100% open. I wanna get to this as fast as I can. So that's gonna go, it's gonna go up like this, and however fast, they're gonna talk about gain in this. Anybody remember gain from high school? So gain is it's your rise over your run. So it's your rise over your run. So the higher your gain is, so this would be like your first number, this would be your second number. So your first number X, so say that's pretty big, say that's like 10, and then my run is 1, that's a gain of 10. And then you can increase from there. So if I increase my gain, and try to go even faster, this line would go even faster straight up. Does that make sense?
That's the slope formula, right?
This slope formula. That's your gain is your slope. So the problem with increasing your gain, while you want to get to your set point of 100 gallons, your stuff doesn't work, or your equipment there's a limitation to your equipment and how fast they can work, right? So if this is my current gain, I'm gonna overshoot my set point, and then I'm gonna come back down, and eventually these oscillations are gonna kill out, right? This happens very quick over time. Like, this isn't hours, it depends on the system. But the goal, like I said, closed loop control, the goal is stability. If you set your gain too high on some of these controllers, it can never find the set point. It'll always be like, oh crap, I filled up too fast. Let me shut the valve all the way off. And then it'll come here. Oh, I'm too low. Let me go. Like it's called increasing amplitude, and it will never find that set point. That makes sense? So if you increase your gain so much, it'll do that. Like ideally, what I was taught in college, you kind of like, you want your, whatever your set point, say my set point's right here, whatever that is, you kind of want to spend a little bit of time, and that way you don't have major oscillations and stuff like that. But sometimes in some areas you have to get there quicker than others, but you have to have a lot better performance out of your stuff, better performance, more money, stuff like that. If I had a tank that had to be at 100 gallons, it didn't matter if I was really at 90 or 110 gallons. It's not that big a deal that I can get to 100 gallons. And a lot of times with these systems, if you ever have a problem with it not getting to the desired set point and can't get it there, flip that joker manual, fill it up by yourself, or fill something up to 100 gallons, and then switch it over to automatic. And that usually gets you close enough to your set point to where your gain doesn't affect it too much. Hopefully that makes sense. But yeah, tendency for increasing amplitude oscillations can be a major limitation of closed loop control. 223, criteria for closed loop control quality. First sentence in those bullet points on page 19 are highlighted. There are essentially 3 criteria for judging the quality of a closed loop control: minimum area, minimum disturbance, and minimum amplitude. Page 20. So we've done feed forward, feed back, or open and close. 230, cascade control. Page 20, all the way in the top right of the page, I've got 3 different highlights. Each sentence at the top right of the page is a separate highlight. So first highlight, cascade control is a modified form of feedback control. One highlight. separate highlight, a single cascade control system has 2 control loops. And then the third sentence, the task of one of these control loops is to maintain the process variable at a desired value. This loop is called the primary or master control loop. Surprised that's going to be some nomenclature that they probably try to change. Because the second loop is actually called the slave. They're not going to go too much longer. Concept, master, and slave. Page 22 and 23. And all of these are just adding more and more control. So you started with feed or open loop control, feed forward. So that has no control essentially. You're just doing the control. Feedback, you're using one control loop. Cascade control, you're using 2 different control loops to make a more fine point adjustment in your process. Page 23, that last paragraph before 240. First sentence in that paragraph, in that last paragraph, the advantage of cascade control then is that the control system does not have to wait for the primary control variable to change before it initiates a corrective action. So remember in feedback, you had to wait for the control variable to change. With cascade control, you don't have to wait for that control variable to change before it initiates corrective action. And the last type of control, ratio control. The first 2 sentences are one of the highlights. As the name implies, ratio control is maintaining a fixed ratio between 2 or more variables. Most common application of ratio control is maintaining a fixed relationship between 2 flows, such as a mixture of air and fuel for combustion control. So usually for combustion control, you have dampeners for your fuel and your air, and it's essentially how your car works too. Like the mass airflow sensor is seeing how much air is going into your car so it can determine how much fuel to put in your car. And it's a ratio, like it's an engineered ratio saying I need this much air and I need this much fuel. Whatever that ratio is, you need to maintain that. So if I push on the gas pedal and I open up my throttle body, that's going to let more air into my mass airflow sensor, and that's going to tell the fuel injectors inject more fuel and keep that ratio the same. Does that make sense? It's probably one of the most common ones. The rest of the paragraph is an online test question. So control is normally affected by adjusting one of the flows, the control flow to follow in proportion to a second flow, which is the wild or uncontrolled flow. So usually you're just controlling one. So it's the immediate next sentence is an online test question. On the right-hand side of the page, that top paragraph on the right-hand side of the page, second to last sentence is highlighted. The ratio relay is simply a manually adjusted gain device. Ratio relay is simply a manually adjusted gain device.
Where is that as well?
Right-hand side of page 23, 2 sentences after where you see the then contracted taps or radius taps. The ratio relay is simply a manually adjusted gain device. Thank you. Page 24. Bottom left paragraph on page 24, first sentence is highlighted. Another common application of ratio control is maintaining a fixed relationship between 2 flows, such as the mixture of 2 materials in a blending operation, figure 21. Blending stuff together, you're going to use a ratio control. Everybody look up here on the board. Let's go through, match the control loop with a scenario. So if I have 2 chemicals that must be continuously mixed together in a specific proportion, what type of control am I using? Ratio. Number 2, a cooling system is highly stable on its own and behaves very predictably.
cascade.
Feedback?
Nope. It's gonna be feed forward. So if it maintains very predictably on its own and it's highly stable, I don't need to control it that much, right? So that would be one, like you opened up that valve a little bit and you just set that output to that valve, however open or however closed you want it to be. You could let it go and that tank would sit at 5 inches or whatever it was. This is the same thing. If something's going to behave very predictably and I don't have to control anything, put control valves and crap like that on it, I'll use, what's the other word for feed forward?
Feedback. Open.
Open. Feed forward is open. Next one, a material must be heated at a specific temperature that must not oscillate. Which one left doesn't oscillate?
Feedback, right?
It's a cascade one. This cascade has 2 control loops, which allows it not to oscillate. The feedback is the one that oscillates. So liquid and storage level must be maintained reasonably close to the set point value, although the tank has the capacity to tolerate some variation. Most common of all those is going to be your feedback loop. All right, that's the end of section 2. I think I'm gonna split this chapter up into 2 different classes. Because I feel like there's a lot of good information in this. So I think I'm gonna make that it for tonight. Go ahead and do those 2 different section reviews. If you like, I can go ahead and give you all the practice tests if you want to go ahead and look at some of those. But read through some of this. Read through that. I think it was like the 3rd or 4th page had the different types of detectors and stuff on that. Like read through some of that stuff and like come back with questions. So that I know I speed through a lot of these chapters and stuff like that, but this is actually a pretty important one that's actually worth reading. So I'll read through this one. So come back with questions and stuff. Does it make sense what I know there's a lot of information. Like that's where I want to stop. I feel like I can only push out so much information at a night. But yeah, if you've got questions on this stuff, like the rest, y'all can take or those 2 section reviews for homework. We'll go over those first thing on Tuesday. But we're done for tonight. I know that's earlier tonight, but I think I don't want to give y'all too much information, not let some of this stuff sit.
I just got to, when you were talking centroid, and then what is like an interference on this case? Like
The oscillating? Let me shut this off right quick. Wait, what? Ask your question again?
Yeah, when you say like the little one at the top.
This?
Yeah, but.
This is the set point.
The set point, yeah, but what is like that?
So this is your control. So this is the signal that you're sending to the valve to open or close. So like right here, let me draw a little bit different. So if my set point is right here, this is my, and I'm at 0 gallons. This is my signal to my valve. So it's saying open, 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 open. I made it to my set point, but it's gonna go a little bit above that. It's gonna say, oh shit, close. Not oh shit. It's gonna say close. You went too far. So close the valve. If it closes the valve, so that's why it's good to have like an analog signal from 4 to 20.
Yeah.
So if the gain's too high, it can send it a 4 milliamp signal saying go all the way open. And if it passes it and the gain's set too high, it can say crap, put 20 milliamps on it and it's gonna go too far down, and that's where you can oscillate like this. The goal is to have your gain turn down enough to where you can just keep going, say open, open, open. We're getting close, so close that valve down a little bit, so that output down a little bit, close that valve a little bit, we're getting close, and then you can get that sweet spot of
Yeah,
55% open is gonna take care of what our signal needs to be.
yeah, okay.
Does that make sense?
Yeah, it's like, for example, I'm driving, right? And
It's like cruise control.
like if I pass a little bit, like I put by the stop, right?
Yep.
In order to get but maybe I can get a little bit, so I just trying to
Yep.
be the same pitch.
And a lot of times, like in the older, I think they're getting better with newer cars, but like cruise control, the gain I've always felt like was too high. Because if it got down too far, I had cruise control on, started going up a hill or something like that, would slam on the gas and even overshoot whatever, if I was setting it at 70 or whatever. That's a closed loop control. Good?
Yes, sir.
Makes sense? All right, I'll see y'all. Y'all have a good weekend.
You as well.
I got a 93,
You got 93?
yeah.
Yeah.
Two
Let me-
questions that confuse me a lot. I mean, I don't know.